Let's see. So thank you very much, Ulrike. And as Ulrike talked about in a couple of slides, there was a small problem with this rod with two ends in a hot and a cold bath. Essentially a heat diffusion problem, one of the simplest PDs we can solve numerically, and it makes for a pretty good hello world example for scientific computing to get us started, prepare everybody's environments for today's lessons, and also get a little bit of a big picture understanding of how these different numerical packages can fit into different components of a computational science application. And before I get going, I want to thank Mark Miller, who developed this problem, these slides originally, and for many years he's done an exceptional job leading the planning efforts for this track. So he leaves behind some large shoes to fill, and I will do my best not to disappoint. To motivate with a sort of a quote unquote real world problem, let's say there's a house with solid walls and a water pipe running through. Of course, real walls are not uniformly solid, but we're making a simplification here, so we can use a constant diffusion coefficient. So given exterior and interior temperature conditions, will the water pipes freeze overnight? We can model this as a one-dimensional heat equation represented by that partial differential equation shown here. Temperature is U, so the partial with respect to time is equal to the diffusion coefficient alpha, which represents how quickly heat can move through the material, times the second partial with respect to space. So we pose this problem in SI units of Kelvin meters and seconds. We set our boundary conditions on both sides of the wall, an initial temperature profile through the wall, and we want to develop an application that will give us the numerical solution for the temperature for all space and time. So first of all, well, there's supposed to be a little error up there, apparently not working, but first of all, what we have here is a continuous partial differential equation. So we have to convert this to a discrete set of numbers in order to be able to write a computer program to solve that. We do this independently on the left-hand side for the time domain and the right-hand side for the spatial domain. The first derivative in time is we approximate with a simple forward difference formula, and we chop the solution time into these delta t steps. We do the same for the right-hand side, except we have a second derivative, so we use this second central difference formula. And we set the discrete forms sort of equal to each other, and we end up with a uniform grid in time and space. So to solve this equation, we would iterate through time with index k and through space with index I. And at each time step, we compute the temperature profile of the wall for the next time step. And this whole scheme is known as forward time central space algorithm. It is an explicit method known to be unstable when this R parameter is greater than 0.5. And I'm sure that many of you have seen this before. It's a very simple problem, but it is the hello world problem, and things will get much more sophisticated throughout your day. So for our first hands-on exercise, we'll just very quickly code up the body of this method. So I'm going to switch out of the slides for now, and we'll actually start with these setup instructions. Hopefully, at this point, you are already on Cooley and your node is allocated. And if it is, you can just copy that and make sure that all of the hands-on examples are now in your home directory. When you go into this, you should see these different folders. These are all the hands-on problems that you will be working on throughout the day. And we're starting today with the hand-coded heat problem. And so here you can see the files. What we're modifying is this FDCS C. Let's see. So here we have this function. We have this function signature. We're taking in the number of discrete points in space. UK1 is the solution at the next time step that we will be computing. UK0 is the current time step, and we're not changing that. Alpha is the thermal diffusivity. We have dx and dt, which define our uniform grid in time and space. And we have the boundary conditions. So the first thing that we actually need to do is to make sure that the problem is stable. So we compute R. And here, this double is actually a overloaded data type, and it helps this code track some performance metrics, but that's the fundamental data type we're using here. So if R is greater than 0.5, we want to return false, right? Because this function is supposed to return false if unstable, and if we detect that, there's no point in doing anything else. However, if things are stable, then we need to iterate over the spatial domain, and notice that I'm iterating from 1 to n-1 non-inclusive. So this is omitting the left and right boundary conditions. We will enforce that explicitly after we compute this. So in this loop, we set this equal to, let's refer back to our formula. It's R times the I plus 1, 1 minus 2R times I, and R times I minus 1. So we can let's see. And then finally, we enforce the boundary conditions. And then we can return true. So this implements the basic FTCS step for our problem. And let's make sure that it actually compiles. And it does. Okay. So we have that. We have our code and it's compiling, but how do we know if it's generating the correct solution? So we could technically do like a method of manufacture solutions, but in this case, perhaps a much easier way is to remember that when the boundary conditions are 0 to 1, the steady state solution is just a straight line from 0 to 1. So we can just run this problem out to a sufficiently long amount of time and test the result and make sure that it is the correct steady state solution. So to do that, first let's take a look at this help here, how to use this binary. This RU name, when you set it, it determines the sort of name of the solution and creates a folder with that name to put solution information into. Our alpha is the diffusivity, length for the spatial, the size of the spatial domain, dx, dt are sort of step sizes. Max t is the maximum time we're solving, and you can see that the boundary conditions are already set to what we want, and the initial condition is just a constant 1. So we can say max t equals 10. Oh, sorry, wrong terminal. So this solved the problem for us. So how do we check under heat results, you can see that there's a folder now. And under this folder, there's this heat results solution file and curve. So we can actually check what that looks like. And this is essentially just information where these are the discrete points in the x-axis, these are the discrete points in the y-axis. So when you plot that, you actually just get a line from 0 to 1. So we're converging to the correct steady state solution, and we can move on with solving the actual problem. We originally said the problem we want to solve is, will our pipes freeze? So the outside temperature, we say, is the outside temperature has been the same for a long time. So the initial condition is a constant 1. There's a storm overnight that drops the outside temperature to -40. Dimension of the walls, dimension of the pipe, and we're going to start doing this with wood as the material at first. And how does the run command for this look like? Let's take a look. So here, I designated run name as wall. Alpha is the diffusivity constant for wood. Our length is 0.25 meters. And this dx and dt have to be selected carefully to make sure that the solution is stable. This R value has to be less than or equal to 0.5. We can't change alpha, that's fixed by the material. And so these values will turn out to be stable, but you can play with this and see where it stops being stable if you like. And this out I and save I, these just determine the iteration counts at which we're outputting or saving the result. So max T is in seconds. So we take 15.5 hours, convert it to seconds, end up with this. The boundary conditions are in Kelvin. So we take the Fahrenheit boundary conditions, convert to Kelvin in this case. And the initial condition is a constant at the interior temperature. Oh, here we go. Let's see. This needs to be put in quotes. There we go. So
Alp, is it
yes?
possible to make your font a little bigger?
Yeah, actually, yes. Is this any better?
The one on the left looks pretty good. The one on the right could maybe use one more step. Okay, thank you.
Yep, no problem. So we've just solved the problem, but how do we check if it's correct? How do we analyze? Well, in this particular case, we have a little plotting tool. If you have X forwarding set up correctly, then this will actually just put up a window. But as a backup, it also actually saves a file. So we can plot that. We're using the same run name as what we used in the actual solution. We're using GNU plot as a plotting tool. I don't actually have X window set up, but I do have so we're just going to look at the plot this way. And so red line is our solution here. This is a temperature profile through the wall. And this line here is the freezing point. So essentially, if our temperature profile is within this black band here, this is where the pipe is. If the pipe is if the pipe temperature is about freezing, then we're good. And here we are, and so our pipes will not freeze in this case. And so you can try with other materials. I can actually go back here, and we can try with the brick and see what happens. In this case, the alpha is going to be 2.7, -7. Oh. So we solved that problem, and we can plot that as well. And the brick is actually even yeah, and the solution for the brick is also within the range that we want. Pipes aren't going to freeze, and so you can go ahead and try this with different step lengths, different diffusivity constants, and see what happens. But ultimately, we were able to do this whole thing from scratch. This does not use any external libraries to do the solution, and that's because we made a lot of simplifications, and these simplifications hide these challenges of developing large-scale computing applications, scientific computing applications. You know, the one-dimension space, uniform grid, solid wall, single material. You know, basic finite difference discretization for the approximations for the derivatives, explicit time integration scheme. But when you get into complex problems with complex geometries and domains, you need advanced discretization tools. You need these scalable linear, nonlinear solvers for large systems of equations. You need better time integration schemes for stability. And that requires a lot of expertise in a lot of different areas. Suddenly, somebody who wants to do this from scratch has to, you know, have expertise in everything from, you know, domain-specific physics to mathematical modeling to parallel programming to, you know, making the code portable for different architectures. And I mean, very few, if any, people possess all of that. And so this is where these packages come into play, that each of these packages are developed by groups of people who have the expertise for those specific tasks, for those specific methods. And there's a great deal of effort in making them portable, scalable, verified. And that is a very effective way that we share this expertise and enable the development of these large-scale computing applications. So that's what today is really about. That you will get exposure to these packages. We're featuring packages in I guess what I call these 4 different, I think, categories. You know, we have packages for structures discretization, solving systems of equations, both linear, nonlinear, iterative, direct, time integration, optimization. And you've already seen this earlier in this talk. I'm putting it up again. And so the first parallel session starts at 10:30. We have 4 of these parallel sessions throughout the day. And within each parallel session, there's 4 concurrent topics that you can choose from. And so this is really intended to be very much a sort of a choose your own adventure type of a thing. And this website up here is your best friend today. However, if you're unsure about what to do, this agenda page also offers some sort of basic like ideas of what you can do. For instance, if you want to just get a little bit of everything, you could do something like this that exposes you to sort of one thing in every category. If you really only care about solving systems of equations, then you can actually get every single package for that. If you really care about discretization, you can get both of them in. Those are both in the mornings. And then your afternoon is, free to pick whatever you like. And if you also would like what I call outer loop tools, things that go around equation solvers, we have those both in the afternoon, and that gives you the morning to choose from. So the next steps logistically is, like I said, attend parallel sessions at 10:30 and 11:45 Central Time. The Zoom rooms for these different sessions are available on the website in the agenda. There's also a dedicated page for virtual meeting rooms. And I want to point out these two special activities. One is right after lunch, we have panel discussion. And so during your breaks and lunch, if you would like to ask any questions to the panel, we have a form for that. You can submit your questions there. And at the end of the day, we also have what we call subject matter expert speed dating. So this is an opportunity for you to pick or identify first, second, third priority individuals who are developing the packages that you care about, and you will hopefully have a chance to meet with them one-on-one, maybe two-on-one, directly ask your questions, have a conversation, and you're supposed to complete those selections by 4:30 p.m. Central at the latest, and we will assign schedules and shortly afterwards. But that's, I think, all I had for today. And I hope you guys have a good time today attending different topics. And I'm going to actually leave that up for another, I guess, few minutes. And like I said, this website is your friend today, and we're all available on Slack, both in the main channel and then the individual channels for the rooms. And yeah, I hope you guys have a good time today. That's all I had today. Are there any questions I can answer in the meantime? I haven't had a chance to check Slack. Oh, somebody's asking what ID I'm using. It's a VS Code. This is and actually VS Code has a remote connection tool, so you can actually SSH into servers and develop on them as if it's local with built-in terminal. It's if you get around to configuring it, it can also do debugging and useful things. But this is a really nice lightweight. I don't want to call it an ID because it's not that feature rich, but it's sort of halfway between an editor and an IDE. And but it's free. It's actually developed by Microsoft, oddly enough. But I would recommend it definitely.
So Al, just to be super explicit, everybody should leave this Zoom, right? And then go to the website and click on a different link.
Yes, everybody, yes. So at the end of this, let me go back to the agenda real quick. So at 10:30, we have these parallel sessions starting. So when you want to join one of them, you can go to the website. We have the agenda here. You can see 10:30 parallel session 1. You can click on these things to read synopses. And when you're ready to join something, you click on the virtual room and then click the meeting link and you can hop into the meeting.
Alp, when does everyone reconvene in the main space? Can you remind everybody?
Yeah, so after the second parallel session, we have 12:45 lunch, and then at 1:45 in the main room, we have the panel. So that is when you need to be in the main room. And then after the panel is done, we are going to once again split to the individual session rooms at 2:35. And then at the end, we will come back to the main room again at 4:35 for the wrap up. Yes, the main room is this Zoom channel, and the slides are available actually. If you go to any particular talk, there's a link right here for slides, and you'll be able to get the slides that way.
So folks, after parallel session breaks and we go to lunch, we will open up the main room again during lunch. So I'd encourage you to connect in advance of the end of lunch so that, you know, we can get people all back in again. Thanks. Okay, so we're officially adjourning in the main room.
Yeah, I think we can do that, and it's 2 minutes to the scheduled